Hello everyone, welcome to this tutorial on getting started with Ray clusters. I'm Hansen and I'll be walking you through a brief overview of Ray. On our agenda today, we'll talk about what Ray is, some features of Ray's AI runtime, and what Ray solves. We'll also go over a typical user workflow followed by a live demo. So what is Ray? Ray is an open source distributed computing framework that allows you to scale out computations across a cluster of computers without the burden of parallelizing your application. As a developer, you can use Ray to take advantage of the resources available in a distributed environment without having to worry about the underlying infrastructure. You get automatic scaling and descaling of nodes, so you don't have to manually manage the cluster as your application's resource and demand needs change. Aside from removing compute restraints, Ray is fault tolerant. With Ray, you can serve and train models in parallel on a remote cluster. If one of these nodes goes down, Ray will automatically send the task to be finished by another machine. On the deployment side, this means that Ray can provide a good failsafe against downtime. In addition to this, Ray also has tools to make state management a lot easier. Ray is flexible in the sense that developers can choose from all sorts of storage options, such as in-memory, Redis, or cloud storage. Ray also ensures that the state of the system is consistent across all nodes at all times with low latency during state updates. On top of the core functionality of Ray is the Ray AI runtime, otherwise known as the Ray AIR. As you can see from the slide, Ray provides an end-to-end workflow for the ML developer with the benefits of parallel compute baked in. You can reduce load-in times from large datasets, parallelize training, and your hyperparameter search space during tuning. Scoring and serving can also be distributed by running inference on different sets of data at the same time, and then allowing the user to orchestrate these results in whichever manner they want. All of these features of Ray can be accessible right from your laptop. A typical workflow for a developer looking to set up a cluster and run compute-intensive code could be something like this flowchart on the screen. You write your code, define this YAML file that indicates how many nodes Ray should scale up to, whether you want auto-scaling or defined scaling, the type of instance, your environment, which would either be Docker, Conda, and AMI, etc. And then you can start submitting jobs and monitor them on the dashboard. The feedback loop once your clusters are up is to just submit your job from a couple of simple commands on the CLI right from your local machine. Before we start this demo, make sure you have the AWS CLI installed and configured with your AWS account. Make sure you also have the correct IAM permissions on AWS to create EC2 instances. If you need help with setting up your AWS account or to configure permissions, refer to the blog post to access links to help you with setting up permissions for Ray. Once that's out of the way, we're going to install Ray onto our system, go over how to set up our YAML, some basic code will run to check that our cluster works, and we'll show the Ray dashboard during compute jobs. All right, so let's get started for the live demo here. So the first thing that we're going to be going over is the YAML that is required to set up a Ray cluster. So I have a sample YAML defined here, which is very basic. And what it will do is essentially start a cluster with a head node. And when I send it compute jobs over, I set a cap of the maximum amount of worker nodes to be 5. So this does not have auto scaling, and it's just meant for demo purposes only. And notice how I just named the cluster name to just be demo so that when the AWS instance starts and the head node begins to spawn worker nodes, it will give this notation for each EC2 instance. So it'll say Ray, the name of the cluster name. So in our case is demo, and then it'll be either head or worker depending on what kind of node that it starts. For here, you can define your cloud provider. So I have AWS in the East region of the United States. And you can also set additional availability zones in the event that all the instances or the region that you want to start these EC2 instances is saturated. So another tip to do when you set up these instances is that you can also enable in the YAML as a flag to do spot instances if you want to reduce your cost. And if you want to look into more of these different fields and flags that you can define in your YAML, there's also a link in the blog post below that will give you a link to a fuller YAML that is defined in the Ray repository. And if you can see here on the screen, this is essentially the YAML that was pulled from their GitHub repository with a lot of different flags that you can use. If you want something even more extensive from this, I also have a link listed in the blog post below that will give you every single field for the YAML depending on what you want to define. So if you wanted to define, let's use Docker images as our environment, let's use Conda virtual environments, anything of that sort can also be found in the documentation, as well as this example full YAML from the repository, which again is posted in the blog post below. For our demo, we're going to use this as a simple way to get started. So I'll continue explaining the YAML here. So we have our AWS provider listed here, and we're going to start listing the available nodes. So I will define a head node as well as a worker node. These names are arbitrary. As you can see here on the bottom, we'll have a head node type. And from here, this is where you define what the head node is. The other one is essentially the worker node. So I have the head node defined, the worker node defined. And in my case, for my environment, I will have an AMI ID. You can find this AMI ID by essentially going over to your AWS console and starting a new instance. So I'll be showing that here. So if I go to my AWS console, I'll click launch instances. I'll be able to select whatever image that I want. And you'll notice that when you click one of these, you'll see on the bottom here, there is a AMI ID right here. And you can take this AMI and just copy and paste it over to the YAML. And every time Ray opens up a cluster, it will install this AMI. So going back to VS Code here, you'll see that I have the image ID, and then I'll also define how big my instance is. So for this case, I essentially set a volume size of 150 gigabytes and the instance type being a T2X large. So once we have the head node defined, you can set authentication. So Ray will automatically create a key pair for you. And the benefit with Ray is that it's very easy to tap into the head node shell. All you have to do in the CLI is type in Ray attach, and then you pass in the file of your YAML. So for instance, a command such as ray attach demo.yaml will actually just automatically connect with your key pair to an SSH session with the head node, and you're able to monitor jobs and look at the worker nodes and things of that nature. So for this example, I essentially just let Ray do its thing, and I'm just giving the SSH user as Ubuntu because that is the default user for this AMI. Now, the next thing that I have here is setup commands. So these are essentially commands that will send to the nodes whenever a new instance is created. So since I don't have a Docker environment or a Conda environment, I opted in to set up a very simple instance where I define the AMI, and then I will send these commands over to set up Python. I'll set up Torch, Boto3 for those who are using S3 buckets and things like that. And then I'll also, of course, install Ray. This command here to sleep is essentially just a quick fix to allow Ray to not skip commands once the instance node has started. This was also mentioned in the documentation to basically allow the instance to sleep a couple seconds, or the SSH session to sleep a couple seconds before sending the actual commands that you want to install. So this is essentially the YAML here. Without the comments, it's a very small YAML, and you can actually modify this at any time that you want. So every time you update this, all you have to do to update the cluster is to just type in ray up demo.yaml. And when you do this the first time, it'll start a setup. But when you do it anytime after that, while the cluster is still up, it will essentially just check to see if the environments are matching. And if not, it will update everything. All right. So now the next thing to go over is some of the sample code that we have here. So before we begin, I'm going to just install Ray, and then I'm going to turn on the cluster. And while that's turning on, I'll go over some of the Python code that we have here for display today. So to set this up, I'll do a pip install ray default. And this is very important to do the default so that you can have all the ray packages. So as you can see here, I already have this installed. Okay, so now I'm going to clear this. And to get the cluster started, all we have to do is do ray up demo.yaml. And you're going to see that since this is our first time setting it up, it's going to say that there's no head node found. And it'll ask you, do you want to start a cluster? I'll say yes. And while that's setting up, we'll go over some of the code that we have here. So there's two ways of issuing a parallel job to Ray. The first is the simplest. So in this sample here, we'll initialize Ray and we'll import it. And we'll set the address to auto. And what this does is based on if you're running this locally or if you're sending this job to the head node, it will just know whether or not to use the head node's IP address and to issue those jobs out to the worker nodes or to just run it locally on your local machine. So going to the function, we have a simple function here. We're just taking X and we're squaring it. And for discrete functions like this that don't require any sort of collaboration or communication between different worker nodes to obtain information from them to be able to do things, you can just send this entire function over to any worker node to do compute, right? So for ray.remote, what this does is that it'll take this entire function and then send this as a job over to a worker node. As you can see here, we're doing this from 0 to 200, and we're just going to collect everything and print the results. So if you want something a bit more intensive and you actually want to see the worker node spawn, right? So in this case, no worker nodes are really going to spawn here. It's just going to run on the head node and it's going to say, okay, this is good enough. So I'm just going to only run on one node. For something more compute intensive, such as this function here that will check all the prime numbers given a certain range, a lower and upper bound, something like this, Ray will automatically know that doing this in parallel and opening up more worker nodes will actually be of benefit. So as you can see here, we're sending, again, using the decorator, ray.remote. We're sending the isPrime function, and we will essentially just send this function over to all the worker nodes. We will collect the information here, and then we'll just print the timing. So in more traditional distributed functions, so anything non-ML related, and if you were to write your own function, you were to do your own data parallelization, every single manual thing that you would need to do distributed computing, using the ray.remote is viable. The problem here is that if you do it in a machine learning context, so let's say you wanted to train an ML model using PyTorch. So looking at this example, you have a lot more to deal with at hand, right? So you have to set up your own data parallelization. You have to set up a way for the model to be parallelized during training, a bunch of other things too, right? So Ray actually has a nice wrapper for a lot of popular deep learning frameworks, such as PyTorch, TensorFlow, you name it. And they have this one single function here. So I'm showing the PyTorch example here. So you can just use torch trainer. You can define the function, the train loop for each worker. You can pass in the scaling config. So for this, I'm just saying, hey, I want to use 5 workers maximum. And you just pass in your training data set. And all you have to do is call trainer.fit, and Ray will automatically handle all the parallelization, the model parallelization, the data parallelization, you name it, right? And doing this allows the user to kind of step away from all the intricacies of driving the distributed training or the distributed application manual mode. Ray does this all automatic, so it's less error prone because the user is not writing this manually every single time. And you're also able to focus on the training aspect or your machine learning application without worrying about the parallel computing side. So now that this is set up here, you can easily attach to the SSH shell by just punching this in. Or another easy way to doing this is, let me exit here. You can also do ray attach and then demo.yaml. So same thing. So Let me go over to the AWS console. So you should notice that in the AWS console, you'll now have a new instance opened and set up. This is running here. Just ignore the terminated ones that was from previous demos. So we only have the head for now, and Ray will spawn new nodes when we need more compute. So let's just start the demo off by just sending the first test. So this one is simple enough, which is taking X and then just multiplying it by itself. So if we were to do Ray submit and we give in the cluster YAML that we're sending this job over to, so demo.yaml, then we'll send over the Python script, so test.py. When we submit this, it's going to fetch the IP, it's going to run the job, and here you go, right? Very, very easy. Only required just one single node, right? Next thing we want to do here is run the second test. So here, something a bit more compute intensive. So in this case, I will show you how to monitor something like this on the Ray dashboard. So let's do Ray dashboard, demo.yaml. When we start this, it's going to connect to the head node. It's going to then forward the port over so that you can view the dashboard on your local host. So let's see here, forwarding port 8265. So if I go to localhost 8265, you'll notice now that there is one node active in this cluster. You can see its memory, CPU usage, and things of that nature. So going back to VS Code, what I'm going to do is I'm going to quickly start this test. And you're going to see on the command line, it's going to start setting up all these worker nodes. And I'll switch over to the Ray dashboard so that you can see it spawning and see all these system resources in real time. So I'm going to open up a new shell. And then I'm going to do the same thing, submit this job. Ray, submit, demo.yaml. I'm going to do test2 this time. So once I submit this, it's going to start thinking, it's going to connect. And now I'm going to switch over to the Ray dashboard here. And you'll notice that all these functions, the isPrime function is being sent out to all these worker nodes that just spawned. On the VS Code side, the shell, you'll notice that it's adding 5 new nodes. And again, it's going to take the YAML and it's going to send all these commands over to set them up since this is the first time. So it's going to do the apt update and it's going to do the Python install just to make sure that every single node is consistent environment wise. So once this is done, it's going to then run the function. So right now, it doesn't seem like it's doing anything since it's still going through setup. But once these clusters are up, they will persist and they will stay up as long as you use them within a certain amount of time if you have this defined in your YAML. So for this, I just have it up indefinitely while I'm running my demo, and any new code that I run, it'll just have the worker node ready and it will remove the overhead, right, since it's already up. So I don't have to install anything. I don't have to set up anything now. Once I submit test2 again, it will actually just run it. So I'm going to just speed up the video here, wait for all the nodes to finish, and you'll notice that it should be able to be finished in due time. All right, welcome back. So now that you see that the job is finished, you'll notice that the time that elapsed was 93 seconds because the cluster actually took some time to set up. But we have our prime numbers here given our range. So if we were to submit this again, I have on the screen here the dashboard with the nodes open. Let's just do a quick submit. You'll notice that the job will run a lot faster this time. So while that's running, you'll see that these nodes will start to have jobs issued to them. And you can actually monitor the processes that are inside each and every single node. So you'll notice that the CPU usage bumped up here. I'm going to zoom in a little bit. You can see inside each and every single worker node, you can see the functions that are running inside, your system resources and things like that. You can actually go to logs too and view all the log printouts of everything that's going on. What's also nice too is if you were training a machine learning model, you can actually log metrics if you utilize that part of Ray as well. And you're able to see, again, each and every single node and what it's doing, what state it's in, and a bunch of other things as well. So this pretty much concludes today's demo. You'll notice that compared to the 90 seconds that we had on the initial run, now we have runs that are sub 19 seconds. And again, the workflow is very simple once you have the Ray cluster up. So again, the initial setup, just installing the worker nodes, getting the worker nodes actually up to speed and active when you actually submit the job. Once you get over that, it's as simple as just making changes to your code, working on whatever needs to be done, submitting the job through the CLI. It'll run compute, return back to you, and you just have this very easy feedback loop with virtually infinite compute on the cloud. So finally, once you're done with all your work for that day, all you have to do is shut the node down. So to do this, it's as simple as Ray down, and you just define the YAML that you started with. So Ray down, you want to confirm to shut this down, and you'll notice that the nodes will then start to kill itself off. And that concludes the demo. And just to be clear, if you have any additional things that you need to interact with the Ray head node, I have also provided additional commands on the bottom of the blog post that allows you to sync files up and down between your local host machine, as well as the head node, as well as interact and just re-update the environments. Without further ado, best of luck setting up your Ray cluster and hope to see you next time. I'll see you around.